So as I say, you're in the Dublin Institute for Advanced Studies, so or DIAS as we call it. So the Dublin Institute was established by Eamon de Valera in 1940, and it is a publicly funded research institute. And tonight's talk is part of our public engagement program. It's called our Statutory Public Lecture. And this particular lecture is for this, what's called the School of Cosmic Physics. There are a lot of unusual names in this institute. And this particular lecture is in association with Trinity College Dublin. And Dave Chu from Trinity, from TCD is here. It's where he disappeared to, but he's somewhere in the audience. Dave, put your hand up there. So before we get into the details of the talk, I just want to thank a few people. I want to thank Emma from our administrator in our section, and Huda as well from our section. I want to thank Robert from IT and Kieran from the house, because it takes a bit of work to organize these events. So tonight's topic is of huge societal relevance. I think it's fair to say that this particular topic sits inside what's often termed a black swan problem or black swan category. It's unpredictable, rare, but of very large impact. So that leads to tricky ways of communicating this type of problem in society. How does one deal with that? So we might get into that later on tonight. I'm delighted that we have Gerard McCarthy giving his presentation from Maynooth University. And following the presentation, there will be a discussion panel, and that's led by Jonathan McCrea. And many people will know Jonathan from Newstalk Futureproof, but he's also from other media events that he's held and from his own media company. So Jonathan's going to lead the discussion and introduce the panel. And then following that, there will be some wine and food. But about our speaker tonight, so Gerard McCarthy, who's, as I say, is in Maynooth University. He did his PhD in Southampton, and then after his PhD, he stayed working at the National Oceanographic Centre in Southampton in the UK. It's one of Europe's or the world's leading centres in physical oceanography. And then he moved to Maynooth University, where he's been ever since. He's a physical oceanographer, and the AMOC has been his main focus of research. He has published many high-impact papers on this particular topic. He's really well known internationally, and he has a very strong research group in Maynooth. And we're very keen to hear what you have to say about AMOC tonight, Gerard. So, thank you.
Okay, thank you, Chris, for that introduction. My name is Gerard McCarthy, and I work at the Irish Climate Research Unit based in the Department of Geography in Maynooth University. And I'm going to talk to you about the Atlantic overturning circulation. So many of you may well be here because of seeing headlines a little bit like this. This was in the summer of 2023, where The Guardian published a headline statement about the Gulf Stream could collapse as early as 2025. So potentially you're here just to kind of refine that down and get a month or a date or set your watches now. So there have been a number of studies like this, a number of studies that have come out that have got a lot of media attention in the past few years. And it really has kind of raised the awareness of the threat of the overturning circulation coming to a halt. Now, I think we're going to start off a little bit more gently than that. So over the course of this lecture, I'd like to take you through the background to what is the overturning circulation, what we think is likely to happen, or what we thought was the consensus in terms of what was going to happen, and how these new studies about the collapse of the overturning circulation fit in that picture. So this is as nice a place as any to start off with. This is the view from my back garden when I was growing up. I'm from Clonakilty in West Cork. And you can see the sea from there. And so growing up, I was always told, well, Ireland gets our mild climate from the warm waters of the Gulf Stream. And in my head, of course, what I was seeing was I was looking out at warm waters that had come directly from the Gulf of Mexico. That was how I perceived it. Now, this perception is not just something that's unique to Ireland. This is a great quote from the Scottish oceanographer Dave Ellett. He said, "In the west of Scotland, chance remarks to elderly ladies upon the warmth of a winter's day invariably bring the reply, 'Aye, it's the Gulf Stream, you know.'" And so Dave Ellett, as an oceanographer, was kind of grinding his teeth about this a little bit because, as we'll see, the Gulf Stream is not particularly unique. The Gulf Stream is probably what has slipped into popular imagination, what the overturning circulation does. So, in fact, I suppose you'll see this in many, many places, this kind of idea of the warm waters of the Gulf Stream bathing the coast of Ireland. This is Garnish Island. So Garnish Island is a lovely little island in Bantry Bay, very famous for the kind of exotic plants that can grow there because it's got a very mild climate. Now, Ireland does have a very mild climate, absolutely does. But bathed in the warm waters of the Gulf Stream, not so much. The little inset at the top will show you there that the Gulf Stream, as it goes across the Atlantic, becomes the North Atlantic current, and it goes off to the north of Ireland. So it's not that we're saturated in warm water that has come from the Gulf of Mexico or the Gulf of America, or whatever we're calling it these days. Really, the water that I was looking out at from Cork was more to do with the Bay of Biscay than it was to do with the Gulf of Mexico. So what is going on, and what sort of things are happening here? Now, I will say that Ireland does have a very unique climate, does have a very mild climate. Oftentimes people will say Ireland has a very mild climate. If you go across the Atlantic to Newfoundland, they have icebergs floating past in the wintertime. Now, that's true, but that's not a very good comparison. If you compare any kind of western coast of an ocean basin to an eastern coast, you get a similar kind of a thing. Basically, in the wintertime, what you get in St. John's in Newfoundland is that you've got cold air that's coming off the frigid North American continent. So it's very, very cold. That's a continental climate. That's more or less what you've got in St. John's. In Ireland, where our winds come from is over the ocean. So, that's the definition of a maritime climate. You have winds that are prevailing over an ocean, which tends to be relatively warm. So comparing the climate of Dublin to the climate of St. John's, yes, we are about 9 degrees Celsius warmer than St. John's in the winter. That's a big difference, but it's nothing to do with the Gulf Stream. It's really just to do with a continental versus a maritime climate, essentially. Now, a better comparison is to look at some place like Seattle. So Seattle is downwind of the Pacific Ocean. And so it is a maritime climate in the same way. It's actually a little bit closer to the equator, so we might expect it to be a little bit warmer. But in fact, Dublin has a climate that is 4 degrees Celsius warmer than Seattle in winter. So 4 degrees Celsius, is that a big number? 4 degrees Celsius, 4 to 5 degrees Celsius is about the difference between the climate of Portugal, the climate of Ireland, and the climate of Iceland. And they're three very different types of climates. So yes, it is a big difference. There's something going on in the Atlantic that is quite unique. What we see is that a combination of the prevailing winds and heat released from the Atlantic is really what gives Ireland its mild climate. So the prevailing winds, the Rocky Mountains actually have a very important role to play with that. So as the winds are coming around the Northern Hemisphere, they bump into the Rocky Mountains and they can't go through the Rocky Mountains, so they either go over it or they go around it. And both of those processes mean that it gets a bit of a curvature. And it means that our prevailing winds are coming much farther from the south than you would typically expect. So we get more southerly winds. So there's a role for the prevailing winds, without a doubt. But there's also a very strong role for the ocean and for the heat that's released by the Atlantic. Now, it's the heat released by the Atlantic. It's not just like a hot water bottle that we're sitting in Ireland. It's the ocean is moving heat and releasing it to the atmosphere, and that's being carried over northwestern Europe. So I want to start kind of at the start in terms of kind of figuring out why the Atlantic is unique. So this is the surface temperature on the globe. So basically you've got warm at the equator and you've got cold at the poles. Climate 101, you've got more solar insolation coming down on the equator, so it's hot. And then more or less all the ocean and the atmosphere, all it wants to do is move it away. So too much heat in the equator will move it up to the poles. That's what the atmosphere does everywhere. That's what the ocean does almost everywhere. Not quite everywhere. And so you get this difference. So Ireland is actually at a pretty far north latitude. I don't think we think about ourselves as a subarctic island very frequently, apart from some circles where we're more arctically focused. But if you were to go to the southern hemisphere, and see an island at the same latitude, you'd be looking at South Georgia. So for any of those of you who are interested in Antarctic exploration, South Georgia is where Tom Crean and Ernest Shackleton and 2 others landed after making it across the Southern Ocean in a converted lifeboat. And that's where they landed. And they sledged across glaciers to get to safety. Still glaciers in South Georgia. Ireland has a much milder climate than all of that. Okay, so what shows that kind of idea? So what I'm going to do here is I've taken all of these temperatures, I've averaged them per latitude. So basically I'm subtracting all the warm temperatures at the equator and the colder temperatures at the poles. And when we subtract it by latitude, this is the picture that you get. So you can look at the cold to start with if you want. The cold happens over big mountains. So you've got cold over the Himalayas, over the Andes, you've got cold over the Greenland ice sheet. Now, when you look at the really, really warm areas, the warm anomalies are really concentrated around the North Atlantic. So stretching from a little bit south of Ireland, all the way up past Scandinavia, up towards Spitsbergen, we're looking at a very warm, anomalously warm for the latitudes that they're at. Up past Norway, you're looking at 10 to 15 degrees Celsius warmer than they would be for that latitudinal average. So the reason for this is, the reason for the Atlantic being unique is the Atlantic overturning circulation. So I'm going to try and call this the Atlantic overturning circulation or the overturning circulation in this lecture. I might call it the AMOC a few times. The AMOC is what we call it in the scientific literature. It's the Atlantic meridional, meaning it's going north and south. Overturning circulation, meaning it's turning over. So what is it? It's a system of currents. So it's not just an individual current. It's a system of currents that include warm, shallow water going northwards, as you see in the top schematic here. This warm, shallow water is pretty salty. It goes up to the higher latitudes, and through a variety of processes, it loses its buoyancy and forms deep water, and it comes back south as a cold, deep water current. Now, the exchange of the warm and cold water is what's really key for the overturning circulation, carrying a lot of heat. Basically, if you move warm water in one direction and pull warm-ish water back in the same direction, you don't get much heat transport. And that's what a lot of ocean basins do. You've got a western boundary current, like the Kuroshio in the North Pacific, moves warm water north, gets recirculated pretty much back to the south again. But in the Atlantic, what you're exchanging is very warm water going to the north and very cold water coming back to the south again. That gives you a large heat transport. It's a key mechanism for distributing heat in the climate system globally. And it's really key for the climate of Ireland, as we've seen already, in terms of the comparison with similar maritime climates. So now I'm going to go back to the same data set. This is our surface temperature data set. And what I'm going to do is I'm just going to fit a trend. I'm going to see how much things have changed over the time period 1900 to 2024. So I've been strict enough in making this plot, and I've excluded any areas that there's over 20 years missing. So that's why you get holes over Africa and South America and Northern Canada. Now, the main signal that you can see here is a red color. The red color means warming. So we know that the world is warming up. This is global warming. This is climate change induced by human emissions of greenhouse gases that's causing the whole planet to warm up. That's the red colors. That's the orange colors. That's not what this lecture is about. This lecture is about that blue spot in the middle of the North Atlantic. The only spot on the planet that is consistently and robustly not warmed, I should say, but cooled slightly, is in the North Atlantic between here and Canada. This is known as the North Atlantic warming hole, and it is a robust feature, and it is very strong evidence that the Atlantic overturning circulation has been slowing down for a while. So how does all of that work? So it works very straightforwardly, really. So we've got the Atlantic overturning circulation moving warm water northwards in the Gulf Stream and other currents, which lead to anomalously warm temperatures between here and Canada and even further latitudes to the north. So when you've got this strong overturning circulation, you get a strong return of deep flow, as shown on the left-hand side here. When that reverses or weakens, you get the opposite sense of things. So you get a weaker northward transport of heat, weaker return of deep flow, and a cool anomaly. And that cool anomaly is what we've been seeing in the North Atlantic over the past 100 or so years. there are consequences to that. So, with a cooling climate, with a cooling area in the climate, we have knock-on effects. So Ireland is very unusual in the sense that, depending on where you start and end it. Now, this is taken from Our World in Data. Our World in Data is a fascinating source of information, but I wouldn't be pinning my hat on the robustness of their calculations very often. It is interesting what they put up here. So this was looking at the comparison of the temperature anomalies in the 1940s compared to the 2010s. And the world warmed up. The world warmed up by about 0.8 of a degree Celsius. 0.8 of a degree Celsius is exactly in line with global warming, climate change associated with the emission of greenhouse gases over this time period. And there was only one country in the world where it didn't warm up, where it in fact slightly cooled over this time period. And that was Ireland. That's not a coincidence. It's because we're right next to this area on the globe where it hasn't warmed up, where it's slightly cooled over this time period. So you can see it there. This is on the right-hand side is a slightly better graph. This is looking at, unfortunately, the colors haven't come out very well on either of these screens. It's lovely on the screen in front of me, actually. But you can see a kind of a cold anomaly to the west of Ireland. That's taking an average over from 2014 to 2023, minus 1940 to 1949. So Ireland hasn't cooled overall, and certainly not if you extend this period. So I don't know why Our World in Data stopped in 2010, but Ireland was very cold in 2010, if any of you remember it. And so if you extend it over a longer period of time, Ireland has warmed, but it's been touch and go over a lot of these periods. Very unusual. And now what we think, so first of all, what I've been talking to you about so far is surface temperatures. That's the data that I've been showing you. So surface temperatures are a robust indicator of what's going on the planet. So there's lots of things influence surface temperature. First of all, we know things are warming globally. That's nothing to do with the AMOC, really. That's to do with the emission of greenhouse gases. In the North Atlantic, there are a variety of processes, but one of the key ones is the Atlantic overturning circulation. And so that is evidence for a decline there. Now, it's not a direct observation of the strength of the overturning circulation. In fact, we don't have very long records of direct observations of the overturning circulation. If you look on the top line here, the rapid array, that's when direct observations of the overturning circulation happened, 2004, 20 years ago. That's the shortest line on this graph. So people put together proxies. So proxy data is something else, such as my sea surface temperature that I was showing you, such as things like when people went out and made measurements with ships, subsurface measurements, you can compile those together to get you a proxy for the AMOC. Such as in more recent years, from the 1990s onwards, using satellite oceanography, using sea surface height and other proxies like that. So this is a compilation of a range of those proxies. And now, I would argue that this says a good agreement between these proxies. Now, it might take you a while to get your eye in on that, but if you follow from the 1990s, you might have better joy over on that screen. So hang on, I'll walk over here. So if we're looking from the 1990s, all of these indicate an increase through the 1990s. After that, there was a decline. There was a dip down here. That was 2010. That was what I was telling you about with this cold period that Our World in Data seem to have ended their graphs on. There was a slight recovery and probably returning to a decline since then. So from about the 1980s onwards, I think we kind of know what the overturning circulation was doing. It strengthened, it weakened, and that's the kind of thing it does. It does these decadal oscillations. It does decades of cool. So we had decades of cool during the 1960s, the 1970s. That had knock-on effects in lots of different ways. The knock-on effects on the precipitation here in the summertime. So the droughts of the 1970s were famous. It had knock-on effects globally because what happens in the Atlantic doesn't stay in the Atlantic. It moves the intertropical convergence zone to the tropical rain belt. That has knock-on effects for a huge range of precipitation effects across the globe. If we go back further than about 1980, we start to run out of proxies. So we've got a couple of instrumental ones that are left. So the instrumental ones are here. So this is sea surface temperature in this blue line. That's what I've been talking to you about. These are paleoproxies, and I'll just talk to you about one of these. This dark green line is what's known as sortable silt. Basically, what they do is they measure the sea floor, the sediments on the sea floor, and when the currents were stronger, they sort the silt out a bit further, and when the currents were weaker, they don't sort the silt as much as that. And so you can get an estimate of the strength of the ocean currents. And these converge in terms of saying that there was a warmer or a stronger period before in the mid-1950s or earlier. Now, this is a much more up and down picture than what I presented you before with this warming hole and with this kind of clear signal of an AMOC decline, of an overturning circulation decline. But it is kind of what we think has happened. This decadal variation is very much a feature of the Atlantic. And we do believe that the most likely cause of this decadal variation is related to fluctuations in the AMOC. An overall trend, well, that depends really on what happened in the middle of the 20th century. So my PhD student Guillaume is in the audience there somewhere there. So he's studying what's going on in terms of the overturning circulation in the mid-20th century. And that's really critical for understanding this long-term decline. The second thing I will say is that the evidence is, coming together that the overturning circulation has weakened. The overturning circulation is robustly predicted to decline into the future. What I'm showing you here are data from climate models. So the past is that black line, that's their past simulation. Their future are these multiple colors here. So multiple colors reflect different emission scenarios. So high emissions, low emissions. As you can see, it kind of doesn't really matter whether you're in a high emissions or a low emission scenario. The thing is going to go down. It's going to go down by maybe 5. This is in Sverdrup. A Sverdrup is 1 million cubic meters per second. 1 million cubic meters per second is about the same volume as all of the world's rivers combined together. So the ocean moves an awful lot of volume around. Easier to think about this as a 30% decline. So we're looking at about a 30% decline by the end of the century. The Intergovernmental Panel for Climate Change, their 6th assessment report that was published in 2021, reports that it was very likely to decline in the 21st century. That's been repeatedly said over iterations. That was the 6th assessment report. Every single one of the assessment reports said the same thing. And you can go right back to the 1980s when they first put dynamic oceans into climate models, and the same thing happened. So you put greenhouse gases into the atmosphere, the overturning circulation weakens. So that is robustly predicted across those climate models. Now, that's not an overturning circulation collapse. That's a 30% decline. That's what is projected. Now, what's been discussed at length recently is the risk of an overturning circulation collapse. So this was from Radio 1 just late last year, covering risk of the overturning circulation collapse. There's also a quote here from then Minister Eamon Ryan, who was discussing new studies that had come out that are talking more about an underestimated risk of an overturning circulation collapse. So what are we talking about when we talk about a collapse? Basically what we mean is that the overturning circulation passes a tipping point and it changes from a situation where it's currently on, robustly on, to a situation where it's off. So in a very simple sense, you can think about that as a seesaw, something like this, where when the ball goes over to one side, it's in a stable state. The tipping point is then when it's halfway between the two of them. It's not that it's completely off, it's that it's going over this point of no return. So you can still have a robust overturning circulation, but you could have passed your tipping point and be past the point of no return. Okay, so a tipping point is something that you're going along at a continuous kind of a pace, and all of a sudden you go off a cliff. There are many, many elements of these in the climate system. For example, Amazon dieback is a very prominent one. So, the Amazon rainforest rains on top of itself multiple times every day. So it's got this loop of raining on top of itself. Now, if you deforest, say, one branch of that, cut down the bit in the middle, and it breaks that chain, then it can no longer sustain everything beyond that. And so you pass the tipping point and you end up with very widespread dieback. I'll give the example of the Amazon rainforest because it's one of the key one of the ones that I think people feel like we're most at risk for in terms of in terms of dieback. There's loads and loads of tipping points in the climate system, just to put you all on edge. There are lots of different ones, and the one we're considering here at the moment is the Atlantic overturning circulation. So the tipping point is a critical threshold. You pass beyond it, and the system shifts. The system shifts into a different state, which is stable. The Atlantic overturning circulation is a tipping element of the climate system. So just zooming in on this part of the North Atlantic, what is going on here that would make it a tipping element? Basically, what you've got is you've got warm, salty water. It needs that salt water to maintain the strength of the circulation. So you have the salt water. If you change it, so say for example, there's lots of ways you could change the upper ocean. You can put a lot of fresh water on top of it. That could come from a melting ice sheet. That could come from a very abrupt change in Arctic circulation with a lot of fresh Arctic water coming out. You could even change the way that this deep water is formed by warming it too much at the surface so that you've too stable a barrier at the top. So there are ways that you can interrupt this circulation, and it's a feedback loop then. So once the surface water is disrupted, then you're into this kind of spiral where you end up with this feedback that can lead to complete collapse. So that's the theory, and a lot of the evidence for this comes from paleoclimate. So we're going to go way, way back in time now with this plot. So this is a plot going back into the last ice age. So we're over there at year 0, essentially. And what we're going to go back is back in time in terms of thousands of years. So you don't have to go all the way back if you don't want to. If you go back as far as YD, that's the Younger Dryas event. That's kind of where we're going to talk about. But back 20,000 years ago, back at number 20 there, you're back in the last ice age. When you go back through the last ice age, you have all these strange fluctuations. So if you look at the last 10,000 years, the very left-hand side of that graph, you see a relatively stable line. It doesn't do an awful lot of wobbling. But when you go back into the last ice age, there's all of these fluctuations. These fluctuations are associated with temperature changes globally of about 10 degrees Celsius. So these were very abrupt climate shifts. They're known as Dansgaard-Usher events, and they are generally associated with switching of the Atlantic overturning circulation from on to off states. So during the last ice age, during a very cold period in the Earth's history, the overturning circulation switched from on to off pretty regularly. The last time there was an event like this was the Younger Dryas event. So the Younger Dryas event was when this last ice sheet was disintegrating, the Laurentide ice sheet, which was on top of North America. So we were just coming out of the ice age, things were beginning to warm up, and the Laurentide ice sheet starts to melt. Huge amounts of glacial meltwater drains into the Arctic Ocean and makes its way into the Atlantic Ocean, shuts down the overturning circulation, and sends us back into glacial conditions again for another couple of hundred years. So these things have happened in the Earth's history, and they've happened. The evidence for it is, well, there is evidence for that in Ireland. So in Ireland, the Younger Dryas event was known as the Nahannigan Stadial. The Nahannigan Stadial is named after Loch Nahannigan in County Wicklow, not a million miles from Glendalough Loch, and it's just down below Turlough Hill. So Turlough Hill is where the ESB has pumped electricity storage. So that's when everybody puts the kettle on at halftime in the All-Ireland final and you suddenly need a big surge of electricity. That's where it comes from. It comes to Turlough Hill. When they were building Turlough Hill, they pumped water up from Loch Nahannigan into this artificial reservoir that you can see. You can see the artificial reservoir on the left, on the right-hand picture, but the left-hand lake there. Loch Nahannigan is the natural lake, natural quarry at the bottom. In the middle of that lake, you can see a very spectacular little ridge, which is a moraine. So a moraine is indicative of the end of a glacier. And that glacier has been dated from the Younger Dryas event. So the quarry that Loch Nahannigan is in is much older than that, but the glaciers grew again during this, what we call the Younger Dryas, when we discuss it in terms of overturning circulation studies. We call it the Nahannigan Stadial when we talk about it in terms of Ireland. So the last time the overturning circulation shut down, Ireland went back into glacial conditions. I'm going to tell you not to think about associating Ireland in glacial conditions with overturning circulation slowdowns, because we're in a very, very different climate than we were in the last ice age. Okay, so I hope those of you that came for this stuck with that introduction. So Gulf Stream could collapse as early as 2025. So this was a study by brother and sister Peter and Susan Ditlevsen in summer of 2023 that estimated the time for a collapse of the overturning circulation as 2057. The 2025 number that the Guardian quoted was like the 5th percentile, the 5th percentile number. So it's probably fair to say that the authors didn't think that the Gulf Stream could collapse as early as 2025, really, in terms of this headline. 2057 would also be pretty bad. 2057 was much, much sooner than anybody would have thought before. So even people who would have talked about overturning circulation collapses would have not really thought about it as anything that's going to happen by the end of this century. So I'm going to tell you a little bit about what Peter and Susan Ditlevsen were looking for in their study. So on the top right, you've got an illustration of a tipping system, right? So this is a dynamic system with two stable states. You can think about one being an on state, the other being an off state, okay? So the ball is bobbling around nice and happily, and then there's some change to the background. And just before it pops into the other well, it starts to wobble. So it starts to slowly kind of repeat on itself. So we'd call that, in terms of the time series analysis, a rising autocorrelation. So it means it's correlated with itself. And that's the kind of indication of passing a tipping system. So if we look at the time series on the top left here, you've got 3 periods. You've got the blue, the purple, and the red. They maybe don't look particularly different from each other at the moment, but if we look at the autocorrelation, so we're looking at how much these lines tend to fall along a straight line between x1 and x2, you can see that the red ones are much more autocorrelated than before that, and that is indicative of a tipping transition. I was looking for a good analogy for this when I was giving this talk, and it's not a bad analogy. So if you sit down in a pub with your buddy and he sits up on a bar stool, and after a few pints he starts to sway on his seat, and after a while he falls off his seat, you can say the collapse is when he falls off his seat. But it was a pretty good indication a few pints earlier when he started to sway. And that's more or less the kind of indicators that they're looking for in these time series of overturning circulation. They're looking for the slow swaying that happens before a collapse. This is the plot from the Ditlevsen's paper. They used sea surface temperature anomaly. So I showed you pictures of surface temperature. I showed you that over the last 100 years, the only place on the planet that has consistently cooled has been between here and Canada. They took that as an estimate of the AMOC for an estimate of the overturning circulation, and they did this wobbling analysis with it. And what they concluded was that it would collapse by 2057. Now that's one study, but there have been a number of other studies, including by Nicholas Boers in 2021, Simon Michel and co-authors in 2022, that have seen similar things in kind of different data sets, to be fair. So this is kind of a signal that has come through in a number of different ones. Now, the Ditlevsens were the only ones that put a number on it in terms of when a collapse might occur. The other ones did indicate that we were closer to a collapse than might be the case. So as I say, they all use this proxy of the sea surface temperature between here and Canada. And so I think this is a robust signal of a slowing down of the overturning circulation, but there are quite a few questions about this. So questions remain about the early temperature records. On the bottom left here are 3 buckets. So if you go back before the Second World War, that's how temperature was measured at sea. You had a bucket, you threw it over the side of your ship, you hauled it on deck, you left it on the deck, and you stuck a thermometer in it and you wrote down the number. That changed through Second World War, where it came to engine intake, where the water was sucked in and measured as it was taken in. But these early records, because of differences in measurement techniques, because of uncertainties around it, are constantly being revised. And there's a paper there by Sippel et al. Who look at the early 20th century cold bias in ocean surface temperature observations that pointed out exactly that. So some of these wobbles that are in this record are due to dodgy buckets rather than dodgy overturning circulation. The second point I'd make is that questions remain about the robustness of this early warning signal. There are people who say that the wobbles in the Atlantic surface temperatures have nothing to do with the overturning circulation. Michael Mann coined the phrase Atlantic multidecadal variability back in the late 1990s, very famous climate scientist. Doesn't think it was anything to do with the overturning circulation. Remember, doesn't actually think it exists anymore, doesn't think it's an oscillation. He says it's all to do with volcanic forcing, aerosol forcing, various particles that get into the atmosphere, change the cooling and the radiative impulse onto the ocean. Even if we say that these wobbles are robustly related to the overturning circulation, there are plenty of times when things wobble like this and don't fall down. You need a certain type of system that would respond like this. So I would take that as a pinch of salt in terms of what I would say about the risk of an overturning circulation collapse. However, it is fair to say that as a scientific community, we are getting more and more concerned about it. This picture is Professor Stefan Rahmsdorf from the Potsdam Institute in Germany, presenting at the Arctic Circle conference a presentation around whether the AMOC is shutting down, whether the overturning circulation is shutting down. Now, Stefan organized a letter that was signed by many of us that warned of the underestimated risks of overturning circulation collapse. Now, robustly, the evidence for that collapse, whether you'd be skeptical about it or not, and I would say I'm skeptical about it, is definitely building up in the direction of that risk being underestimated at the last time the Intergovernmental Panel for Climate Change assessed it. And so what this letter called for was to initiate an assessment of the significant risk to the Nordic countries and to take steps to minimize this risk as much as possible. Now, this said the Nordic countries, but as you saw, if you remember the figures of where you had the lovely warm temperatures up by Norway of 10 to 15 degrees warmer than the latitude, but that starts down in Ireland. So Ireland is as much a Nordic country in this context as the Nordic countries this was presented to. So what would happen if the overturning circulation collapsed? So cooling is the one that people talk about a lot. And if you're going to take one thing away from this, don't talk about cooling. So this is what you see when you shut down the overturning circulation. So these are experiments that are done where you simulate a melting ice sheet. You simulate a load of fresh water going in on top of the North Atlantic. You shut down the overturning circulation, and yes, you get a lot of cooling. This is not our present planet. This is not a planet where we're warming in the background due to global warming. So you do get a cooling in this context, but these are just idealized experiments about what happens when the overturning shuts down. Not actually a future estimation of what's happening in what is a warming world. The change then, you also get a knock-on effect for things like precipitation. So precipitation robustly results, a slowdown or collapse in the overturning circulation robustly results in, for our part of the world, less precipitation, particularly less precipitation during the summertime. In fact, it's not really, the worst impacts of precipitation changes won't be happening around where we are. You can see the biggest colors on the left-hand side in around the tropical rain belt. So it shifts to tropical rain belt up or down. You get an impact associated with wind strength anomalies. So you get increased storminess. The overturning circulation. So again, if you go back, I showed you that picture of the temperatures on the surface of the globe where the equator was hot and the poles were cold. So basically that equator to pole temperature gradient is like an elastic band pulled tightly that that can ping storms across the Atlantic. And the overturning circulation actually smears that out. It pushes more warm water to the north. So if you shut it down, you tighten that elastic band, and you get more wind strength anomaly coming in the direction of the UK and Ireland, which is what's shown on the right-hand side. Still in the realms of collapse, I would say where we will feel it most sharply would be in precipitation change. This is a study based on arable farming in Britain, estimating that the change in precipitation in response to an overturning circulation collapse could end arable farming, or end the viability of arable farming in huge swathes of Britain. So AMOC maintained on the left-hand side, you've got plenty of rainfall. AMOC collapse on the right-hand side, and the whole eastern side of England and eastern Wales is no longer viable for arable agriculture. That's a pretty big deal. So there's two things. So first of all, there's the impact of an AMOC collapse. Second of all, there's the impact of an AMOC weakening. So they're two different things. A collapse is something that is still considered to be not very likely, although we are revising the likelihood around that. The second one is an impact of an AMOC weakening. That's something that we think is very likely. So you're not escaping an AMOC weakening, even if you escape a collapse. Now, the impacts in terms of precipitation and in terms of wind are very similar. So you get a drying in and around UK and Ireland for a large AMOC decline like this. And again, you get the knock-on effects for the tropical rain belts. The right-hand side is a cross-section through the atmosphere with latitude along the bottom. So if you want to just go to Ireland, you want to go for about 50 or so. So that's about the middle of that red line there. And so that's telling you that the jet speeds, the jet stream overhead is increasing very much, and you get stormier winters. Now, I told you to stop talking about the temperature effects of overturning circulation. And the reason for that is because the world is warming up. So if you think about the temperature effects, these are two scenarios. One on the left is where you get a large AMOC decline. One on the right is where you get a small AMOC decline. But this is in a warming world. So you can see the world is warming up. But on the left-hand side, you can see a large AMOC decline in and around Ireland. You end up with a change not far from zero. Now, this isn't some kind of Gaia hypothesis where everything is going to be all right in the end. And Ireland is maybe one of 2 or 3 countries that's going to just escape the worst of the warming because of this. But I would say it's not worth talking about temperature. You may have noticed that we don't suffer that badly from heat waves. Heat stress is not the biggest climate threat to us in summertime. But when you think about things like precipitation, when you think about things like storminess, I mean, with the week we've just had, increases to storminess is a big deal in Ireland. Changes to precipitation is a really big deal as well in Ireland. So we manage our water in a very particular way in Ireland. We use surface water. That's not really the case around the globe. Surface water means it has to rain kind of all the time for you to have enough water. So it's always frustrating where, you know, it rains for 10 months of the year and then you get 2 months of drought and you're on a hosepipe ban. And that's what happens in Ireland. And that's because you need a certain supply of rainfall. So drier summers is a real challenge to exacerbate what's happening in terms of climate for Ireland. But no day after tomorrow here in terms of an AMOC weakening. That's a clip from the day after tomorrow. That was a film which is 20 years old now at this stage, about the overturning circulation shutting down and an ice age happening in a day or two, I'd say. So a good way to think about the overturning circulation is to think about how it happens in the context of a changing climate, right? So temperature, what's happening with climate change and temperature? It's increasing generally around the globe. An AMOC collapse would lead to a decrease locally. So that would actually lead to a mitigation of temperature effects in and around Ireland. So temperature, don't worry about temperature, but that doesn't mean you don't have anything to worry about. As I say, precipitation, the impacts of AMOC change in terms of precipitation and storminess is an exacerbation of the impacts that are happening with climate change. So a summer decrease in precipitation is exacerbated by an AMOC collapse, an AMOC weakening. Storminess, you have fewer and bigger storms in the climate change scenario, you get a stormier, you get a supercharged jet stream. with an AMOC collapse. So you get an exacerbation. I'm much more worried about the impacts of precipitation and storminess than I am about heat extremes in Ireland. So I would say this is where we would want to focus really in terms of what should we do. So one of the questions is, well, what are you going to do about the AMOC? What are you going to do about a slowdown of it? So first and foremost, action on climate is the most important thing that we can do. So action on climate is, is very straightforward. It's a technologically feasible problem. And so we just need to get on with dealing with it. Oftentimes people say, but we're just a small island. We've only 5 million people. And even if we're good boys and girls, and what's going to be the difference if nobody else is? Well, I think you can always ask the question about how you adapt to things as well. So you build in so for example, any large major public building built in Dublin takes account of a sea level rise of 66 centimetres. That's a built-in adaptation to climate change. So the question you would want to ask then, so sea level isn't a great example, but let's go to a water infrastructure. If you say we need to deal with droughts of X amount for future summers, if the AMOC collapses, you go and extend that by a bit more, and you ask, are your adaptation solutions robust to that? Are they scalable? So that's what we need to do in terms of understanding the impacts and understanding our response to the impacts. So that's more or less where I'm going to leave it. Whether the overturning collapses or declines, Ireland is facing drier summers, stormier winters, and somewhat changed temperatures. So what we really need to do is adapt for a range of future scenarios and deal with the future climate that is coming our way, whatever that is. So thank you very much.
Thank you so much, Gerard. So, as we mentioned, Jonathan McCrea is going to take over. He's going to chair a panel. We have, and he's going to introduce the panel as well. We have connection in from Galway. We did have another female panel member who was supposed to be here with us, but unfortunately got pulled out. But I don't know if we've got the Galway connection.
Do we have access to Caroline?
Yeah, I think so. Is she there?
Are you there, Caroline?
So, Jonathan, it's all up to you.
Thanks very much, Chris, and it's great to be here. Really fascinating subject. Thank you so much, Gerard, for really giving us quite a comprehensive view of the subject. But we're joined by two other speakers who are going to have a discussion with us about how this might impact Ireland, modelling and so on. And so I'd love for you to be involved. So raise your hands as soon as you have a question in your head. We'd love to get your thoughts. This is a public lecture. It's for you. So please don't let me do all the work. So we're joined by Dr. Caroline Cusack on the line. She is a biological oceanographer, and she's the leader of the Ocean Observations Team at the Marine Institute of Ireland. Her work spans from deploying oceanographic equipment to deploying climate services that protect marine ecosystems and support sustainable marine activities. And her expertise is in ocean modeling and data analysis, which gives us insight into how our oceans are changing. And we're also joined by Dr. Tito Semler, who you might know from his TV appearances. He was on a TV program we did not too long ago. He's a senior research fellow at Met Éireann, and he specializes in climate modeling with a focus on the North Atlantic. And his work is really instrumental in refining our understanding of how the AMOC and the changes in the AMOC may affect Ireland's climate in the future. So please welcome our extra panelists, please. Now we're going to try this thing, Caroline. We're going to try and connect with you. So we'll see if this works. Okay, but you can hear me all right, can you, Caroline? Yeah. Great. Okay, so you might start off explaining a little bit about your work and what the difference is between a physical oceanographer, which is Gerard's work, and a biological oceanographer, please.
Okay, so oceanography.
Yeah, that's if you turn off your speaker for the moment.
did, yeah. Does that sound better now? Sorry about that.
Go ahead.
Okay, so oceanography spans many disciplines. So anyone who's studying the ocean, right? There's so many different job opportunities for people, right? So I would be a biological oceanographer. You can have a chemical oceanographer. You can have a physical oceanographer like Jared, and then you have like Tito there. He's a modeler, so a numerical modeler with the virtual reality where he's doing a digital twin of the ocean. So a biologist, my background originally was focused on the pelagic system in the ocean and microscopic plants, but I work really closely with the physical oceanographers and the chemical oceanographers because I need to know the information in order to see how that impacts life, right? So I moved on in my career and I did an awful lot of work with downstream services, working with people to co-develop something that might be useful to them, like a warning system for the aquaculture industry, which mixes all the disciplines together. And then recently we started looking at climate services, which is so important at the moment. And George will tell you, he's come to see with me and he say, I have to stop saying I'm a biologist anymore because I actually know a little bit about physics and I'm learning all the time. So the talk was great. Thanks very much.
Okay, very good. You might need to turn your speaker back on to be able to hear us, or maybe you can hear me through the phone, actually. So tell me a little bit about how changes in the AMOC that we heard from Jared, how might that affect marine life and things like phytoplankton and algal blooms?
Okay, so, so we did a study already on co-developing climate services actually focused on harmful algal blooms, and we found that we use machine learning, we use the physics, the numerical models for projecting into the future a couple of decades. So a lot of people in Ireland, they find it very difficult to see like 100 years time or 50 years time. So they want to know within their own lifetime what's going to happen. So especially industry or people who's going to impact their livelihood, and do they need to diversify? So we did a study looking at the up to 2035, and we saw that in certain areas, certain species will increase, whereas in other areas it doesn't. So that's really important for people to remember. So not every single area is going to be impacted in the same way. So it's really important to become aware and knowledgeable about the information so that you can actually take, action to kind of prepare for that. But now recently, we've been planning to connect the fisheries guys and the physical oceanographers, so like Jared's group and another group from another university, to try and pull together the information from both the physics and the fisheries, because although fish don't eat temperature and they don't eat salt or salty water, they do eat the organisms that are impacted by these changes in temperature and salinity. So if you're going to get a massive change, you'll have, just like inland where you might have moss growing in certain place because it might be damp, or you might have another daffodil, say, growing somewhere else. It's the same thing in the ocean. So you're going to have total change in the system. So your fish or any organism that's dependent on these little organisms, the grass of the sea, say, they're going to have to move. Okay, they can swim, but they're going to have to move to where the actual conditions are right for them, so their ecological niche. And so there's been a little bit of work done by some colleagues in other countries, because we don't just work alone in Ireland, we work internationally as well. It's very important to determine, like, say, simple numerical models looking at the temperature and salinity signatures and how that certain fish species would actually, like to sit in a particular water type. And that type of information is going to be so important in the future when we get the predictions in from the modelers to be able to advise for fisheries, say, for example, on stock assessments.
Caroline, thank you very much. We'll come back to you in a bit, but I wanted to bring in Tito because while lots of oceanography deals with observations, yours deals with models and looking into the future. Can you tell me, with something so complex as the Atlantic Ocean and all of the things that happen, including different currents, the surface temperature, the air temperature, depth, and so on, how on earth do you model something into the future with accuracy to be able to predict how this AMOC may change or how it might affect Irish climate?
Yeah, well, and what we are doing is we basically divide our globe into grid points, and we simulate for each grid point both vertically and also horizontally. Basically temperature and salinity in the ocean, or temperature and humidity and other parameters in the atmosphere. And it is, of course, a challenge. But having said that, the models have actually done remarkably well. If one compares from 1850 to 2014, that's how we test our models in the IPCC framework, like CMIP framework, the Coupled Model Intercomparison Project, has done a remarkably good job in the basic quantities of the climate. And that actually includes at least the mean AMOC strength that has that also declines by a little bit less than a sphere drop per decade, both from observations and also from the models in the last decade. So, but what you are, of course, talking about the challenges that we have, because some of the scales are much smaller than these grid boxes. And that implies, of course, that we have to put extra emphasis in our model on the small scale structures that, for example, occur in the ocean in very narrow boundary currents. So we actually refine our mesh in a very modern generation of our climate, of one of our climate models, I should say, so that we can actually really simulate these very narrow boundary currents that are really crucial also for the Atlantic Meridional Overturning Circulation, the AMOC. So, and of course, that is important because the AMOC is not just one number, that it decreases over time. I think that is kind of agreed already, that between all this, even the not so fine resolution models, that the AMOC will decline in the future. But of course, if we put in these extra precise simulation of the boundary currents, we can also see that the AMOC is could be regionally differently declining. So for example, the eastern branch could decline less or could even increase, while the western branch could collapse. So there's also the possibility of a partial collapse. And that, of course, is very crucial for the Irish climate, because, of course, which branch collapses, or if only if the whole thing collapses, makes a huge difference on the climate of Ireland. And that's what we are actively working on, basically refining our global climate models. But then at the same time, we are also running, that's a second important strand in the climate modeling unit at Med Erin, that we are basically doing regional climate projections, where we basically can then in the future, that is planned, we can feed in scenarios where we have a strong AMOC decline or a weak AMOC decline, and also where one part of the AMOC may decline very strongly and the other not. And we can feed that into our regional climate model and have very precise information in the regional climate, what that would mean for Ireland, that we also call storyline scenarios, because depending on, of course, the regional manifestation of AMOC decline or not AMOC decline, the differences would be different for Ireland. But so it's two strands really. One, to refine the global climate model and to reduce the uncertainty, so that we can actually get more trustworthy climate projection. And the second strand is to study the impacts on the Irish climate in a high resolution through the regional climate modeling approach.
Yeah, so a regional climate modeling gives us a really a narrow view of what's happening in a particular area, and you want to reduce your error of your margin of error to try and say, well, it's most likely going to be something like this when it comes to modeling. How far, Jordan Peterson was on Joe Rogan recently, was saying, once you go into like a week in the future, you can't tell anything about the climate. So I'm wondering how do we know that our models are robust going 10 years or 15 years into the future?
So basically, the only way we can know is that we make a very thorough comparison between model and observations. So, and really see, that's why we also really need very good observations, especially in the regions relevant for the AMOC. And also around Ireland, we need really good observations so we can actually refine our climate models and really say they are getting better. Of course, then the trustworthiness or the confidence for the future climate projections increases.
We're going to go to your questions in a second. So do raise your hands. We'd love to hear from you if you have any questions for our panel. I just wanted to ask you, Gerard, about the language, because the language is an important part, isn't it? As a communications guy, I'm fascinated by the language. And this term collapse is a very frightening one. But when we think about it, you didn't actually mention it there, but one of the most interesting things about the AMOC is that it takes 1,000 years for a parcel of water to complete a full cycle, right? So we're talking about something that moves very, very slowly. When we talk about collapse and tipping points, what is the time frame in which we see the step change from here to here or here to here, depending on how you frame it?
Yeah, decades to centuries is basically the short answer. So you can take the more extreme scenarios like your Ditlevson paper, which has it in, 30 years time,
And that looks like what? If we're talking about collapse, if 30 years time, a collapse looks like what?
That looks like zero overturning circulation. That looks like a relative reduction of the mean temperature of Ireland by about 5 degrees or so. And so that's quite a different world to be living in.
Okay, in what respect can you visualize what that would mean?
So I think, as I was saying, I think it's very important to think about these things in the context of background climate warming as well. So I think the type of large overturning circulation decline that I showed in the last few slides is probably representative. So you would probably not get a major change in terms of temperature around here. You get the opposite effect then for the rest of the globe, where you get exaggerated warming associated with an overturning circulation slowdown. But the impacts then on your precipitation and on your storminess exacerbate what's already going to be getting worse in terms of climate change. So you're talking about increased drier summers and stormier winters, and those two things are much more difficult to adapt to.
Okay, do we have questions from
The audience, please raise your hand. There's one gentleman at the back and one here. We'll start with the gentleman closest. Yes, go ahead.
Yeah, I'm just wondering about the interplay between the jet stream and the AMOC. Very briefly alluded to it.
Yeah. So there are observations. There are observations that have shown that the jet stream has moved farther to the north in response to a decline in certainly in the temperatures of the Atlantic, probably related to the change in the overturning circulation. So we would expect that the jet stream would get stronger, shift a little bit to the north. That's what we expect to happen in response to a decline in the overturning circulation.
Is there any feedback loop there?
There is a wind-driven element to the overturning circulation, definitely. So as the winds shift, then that affects where the currents go around North Atlantic. So there is definitely that interplay. It's not thought of as a kind of a tipping point type lock where you would get a feedback like that, but there would be an interplay, yes.
Yes, gentleman back.
So we've been told, I've been informed, that if we have a 6-degree variance in temperature, which could happen by 2100, that the ocean volume water level increases by 6 to 8 meters. And hence by 2057, if you get 4 degrees increase, then probably 10 feet above us. And of course, the rainfall will increase potentially the same. But you've introduced a new dynamic into this now today, and you're saying that all this warm increase in the temperature, let's say by 2047 by 4 degrees, then suddenly it has to drop down into the deep ocean current. And hence, the water is warmer going into that deep water of ocean current. So it doesn't go down to the same depth. And if by 2057, does that temperature of the deep water current increase by 4 degrees? Or does it remain what it is today? Or what happens to it? Or does it buoyantly move up 100 kilometers up and start to put it 100 kilometers above?
So in terms of kind of observational comparisons, you'd probably want to go back to like the end of the last ice age when the overturning circulation was distinctly weaker. And that was a time period where you had less of that really deep water going back to the south. So that is the kind of reorganization of the ocean circulation that you would get. But I just want to come back to your numbers. So a change of 6 degrees by the end of the century is very, very high end in terms of temperature change globally. The sea level rise you discussed was also very, very high end in terms of what we expect to happen. So we're expecting something more like, on the high end scenarios, we're expecting more like a meter of global mean sea level rise by 2100, not 6 or 7 meters. There's plenty of ice to melt in the world, and if we keep warming the planet, it will eventually, a lot of it will melt, but that's not the kind of scenarios we're looking at by 2100.
Okay,
sorry, I just want to bring in Caroline because you've been waiting for a while. Sorry,
If you don't mind, I'm the chair. I will come back to you if that's okay. So, Caroline, as someone who looks after the Ocean Annual Survey, I wanted to ask you your experiences of what you've measured and observed off the coast, and whether or not any of that ties into what we've been talking about this evening with the AMOC.
Are you there?
I think did you mute yourself?
Oh, yeah. Can you hear me?
Yeah.
Okay, cool. Sorry, I muted myself because I didn't want to be making noise. Yeah, sorry. Okay, so the first thing to remember is one of the slides that Gerard was showing you was saying that the time series is quite short for the observations, and Tito was telling you how important the observations are in order to have really good models. So our survey goes back to about 2004 when physics was done, and then in 2011, 2012, we started bringing the chemistry. So we would have a small time series, but we're already seeing changes in some things based on the results coming out. So an example of that would be we take the chemists take measurements for DICTA, so it's like to do with ocean acidification. So we've seen that there is a change, and so the ocean acidification pH has dropped offshore. And what's concerning there is that we have coral reefs, believe it or not. It's not just Australia. We have cold water coral reefs at depths offshore. And ocean acidification, it impacts the development of their outer skeleton or the shell. The same thing for oysters would be the case. So the larvae need to use more energy to build their structures. So you're taking more energy to do something, which is not very good. And also there's a dissolution as well if it gets too bad for them. So that's an important finding. And then the other thing is that we are part of a global ocean observing system, and the information that we collect is part of the global shipboard platforms around the world called GoShip, and we collect data to the highest quality standards based on they have rules that we have to follow. So the information that we collect goes into kind of combined global information. So that's quite important. Plus we also feed into IPCs, which is the Gerard, you'll have to help me here now because I always forget what acronyms. We live in a world of acronyms, science.
Yeah.
Politics, but anyway, it's to do with the North Atlantic observing, and an awful lot to do with fisheries, but also all biology and physics and chemistry, right? And we each year we come together and we produce a report called the the IC's report on climate change, which is quite important as well. So they're just a couple of examples, but we also feed in to directive-driven stuff from the European Union and from our own government. Yeah. And one of those would be the Marine Strategy Framework Directive, making sure that we check the health of our ocean to see if the quality has deteriorated or not. And so this information is quite important for that kind of reporting. So is that enough for you?
No, that's great. Well, I just wanted to ask you one follow-up on that, and that is, I'm conscious of time, but we look at climate change and its effect on things like algal blooms. I know that's some of the work that you've done. Do we anticipate that if we see a decline of AMOC, that we might see, a significant change in this type of plankton, and therefore a knock-on effect on species that can't adapt very quickly? Might we see large extinctions of species because they can't adapt to rapid change if we do see something like that?
So that's a huge question. Okay. Globally, actually, with harmful algal blooms, there hasn't been a massive change, right? Because there's been a massive change in aquaculture and actually monitoring. But certain regions of the world, like I was saying earlier, it actually is changing. And so biology is so complex and complicated that I couldn't answer that question. I'd need to have a crystal ball to answer that question because of the complexities of the physics, the turbulence, and the changes. Like organisms, the big blooms that you'd hear about, red tides, they happen when there's really stable water and it's warm on the surface. And things like marine heat waves, which is not related to the AMOC, but is related to climate change, would probably impact on having more blooms. But the AMOC itself is for me, I can't answer that question.
No, that's okay. I did put you on the spot, so sorry. But thanks very much for that, Caroline. Do we have any other? Yes, question.
Jared, thanks for a very interesting talk. I think you described the AMOC collapse as a black swan event, then went on to discuss kind of more definite scenarios of the AMOC weakening. I wonder if we stay in the realm of what's, we're more certain is going to happen. What's the rate of weakening, say by 2050 or 2100 within the next 52 to 100 years, and what are the expected impacts of that?
Yeah, so the kind of consensus for the climate models is about a 30% weakening by 2100. The impacts associated with that.
Has that been recently? Wasn't there a recent paper you were saying that sort of questioning the rate of decline?
No, I would say the multi-model mean of the climate models has it around that. Okay. Yeah. Now, each individual model is different, and you can get a range, and depending on how you constrain or weight your model, you might get a different answer. But that's the kind of consensus that we're looking at. A lot of the impacts are the same, just scaled in different ways. So the drier summers, the stormier conditions, the relative cooling, these are all present in the same way for an overturning circulation collapse. You get it in a more extreme sense. For the 30% decline, you get it present, but not as dominant. So it's interesting that there are, certain climate models, when you run them into the future, you can see that warming hole develop as the overturning circulation weakens. But you're looking at kind of those kind of effects, but not quite as extreme as a collapse, basically.
Great. There's a lady there at the back.
You showed the graphs that had a 10-degree fluctuations during the last ice age. What kind of time period are you talking for those 10-degree fluctuations?
Yeah, so you're probably talking about centuries type time scales there. Now, the last ice age was very different from the climate we're in now. So the existence of complete collapse of the overturning circulations in past warm climates is not as common by any measure at all. So during that very cold period, during the last ice age, you had this big fluctuations of the 20 degrees. We wouldn't really expect the same kind of fluctuations in a planet that has an awful lot less ice, basically.
The gentleman in the red jacket there, yeah. Go ahead.
Hi, my name is Manan. I am here from the 3D Business School. I'm studying the program Responsible Business Sustainability. I don't come from the world of climate, but more come from the world of ESG.
Yeah.
There's a huge gap which I feel is there between communicating the importance of this to businesses today. Where you mentioned about climate action, a lot of it needs to come from there, most, if not all. Do you know of any resources or ways that businesses can realize, one, what actual impact will this have, including global corporations, because there's going to be a lot. And two, how do you effectively communicate this? Because that's the need of the hour.
Yeah.
So, depending on the corporation, it's potentially easier or more difficult to communicate with. We could take something like an insurance industry. I think insurance industry deals with risk very frequently. And when we speak to insurance industry, I think they understand the kind of things that we're talking about conceptually. What's the analogy in terms of how you convince people that it's worth preparing for is, maybe a collapse of the AMOC is a small probability event, but that could be the same probability of your house burning down, whereas you probably have insurance to insure against that. So I suppose that's kind of a communication element. But I think, as you rightly point out, the biggest corporations in the world are the largest polluters in the world, and it's a massive challenge to stem the tide there. And I would say this kind of goes straight into, this isn't necessarily about communicating about AMOC, this is communicating about climate change. And, the kind of the push from, say, large tech towards AI and energy intensive data centers is all going in the wrong direction, so it's a real big challenge. I don't have a satisfying answer for you, I don't think, really. I think it's worth remembering as an individual that yes, there are things we can do in terms of action on climate, but it's systematic change is going to solve this problem, and that's at governmental and that's at large corporation level. So continuing to put the pressure in that sphere is the way to solve climate change. It's, for example, carbon footprint. That was invented by PP. So, that was to take the pressure off them. It's not big oil is digging the oil. It's not big oil is polluting. It's you. So remember that.
Tito, Met obviously have a huge role to play in communicating climate and really impressing upon businesses and individuals that there's something we need to think about. I was reading today about a meteoroid that has shot up to 1.4% possibility that it hit Earth, right? Which is 1.3, which is the highest we've had in decades. So this meteoroid has a 1.3 chance of hitting Earth. And I read with interest that agencies across NASA and across global agencies were swinging into action to figure out what to do about this. And I got the sense that certain disaster scenarios are sexier than others, because we've known about this AMOC collapse for a while, but I don't see lots of agencies swinging into action to prevent that. And so, Tito, tell me a little bit about the communication of this. How do we get it right? Because it's hugely dangerous to over threaten and make people feel like this is an immense danger, because if it isn't, that you'll lose credibility. But at the same time, you need to communicate risk to an audience that typically doesn't understand risk very well. So how do you do that?
Yeah, well, I think it is, of course, right to say that, for example, one wouldn't want to board an airplane when one knows there's a 1% risk that it crashes. And so you could also say, since for example the AMOC, even if there's only a small risk it collapsing, but if it has a very severe consequences like more extreme events and really a change of seasonal cycle, which we are of course investigating in how far that will be the case based on our model results. If we communicate this, then at least the general public can get a comparison. And it is of course, obviously we cannot really push people into action, but we try, of course, with the communication to make some comparisons and to see how we can convey the message best. So the thing is, we are, of course, all trained as scientists and as not really as communicators. So we are also seeking help, of course, for that to make a consistent and effective communication.
Right. If only there were people in the room who might be able to help with that. Philip, would you like to say something about that?
There's more noise in my head over this subject than anything else in this area. But fortunately, I had a conversation with Gerard early on this week, and he quieted all of that noise with the answer to one question, which I think might be useful for people to hear now. Because the reaction, the backlash from the Guardian headline that you showed earlier on was something that ended up generating a slew of contradictory headlines suggesting, no, AMOC is stable, or no, AMOC doesn't actually exist. There is no coherent currents throughout the North Atlantic doing what we say AMOC is doing. I asked you, are you able to reconcile and hold in your head a model where the Ditlevson's research predicting a tipping point in 2057 and research like Dennis Volkov's in Florida saying, no, the Florida current is stable? Are you able to hold both of those scenarios in your head and say, yeah, no, they don't contradict each other?
Yeah, quickly now.
Yeah, so the short answer is yes.
Okay, great, thanks.
So more or less, Dennis Volkov did a very good study about revising the estimates of the strength of the Florida current, and the result, when it was fed into the calculations of the overturning circulation, meant that there was a decline of about 1 sverdrup, so 1 million cubic meters per second. That decline has happened over about a decade. Sorry, 1 sverdrup per decade is what is there. The Ditlevsons used a sea surface temperature-based proxy, which completely agrees. I showed one plot there with all these plots on the same line. They completely agree. And it's important to kind of bear in mind different timescales that you're talking about. So these, that Dennis Volkov paper sits neatly within that, but they were asking different questions and trying to answer different questions with these studies. And I think that's an important point. I'm not sure if that's what I answered your question when you asked me during the week, but
okay, very quickly, Chris, I wanted to ask you a little bit about can we measure the AMOC through some clever means? Because you were telling me about some very clever stuff with fiber optic cables, and I want to hear it, please.
Well, I wouldn't like to go quite as far as saying we can measure, but I mean, it's really a question that it's related. There's a related question that is, so we hear about the models, we hear about the data, and there's a lot of uncertainty, and it goes back to, I really like this question from the gentleman at the back. It's about, so that to me asks the question, how do we reduce the uncertainty? So what do we need to measure in order to reduce the uncertainty? And so that comes to your question. One of the things that my background is in seismology, where people have used optical fiber cables as ground vibration or ground temperature sensors. And the thing that we've been doing of late is trying to develop systems which will allow us to use transoceanic commercial optical fiber cables as ocean sensors. Very much in its infancy, and it's a thing that's developing in a few places around the world. But that's, it's a little bit off. But the question is that a sort of thing of any value to try to get additional measurements from the deep sea? So what, I guess the question to the panel is, what do we actually need to measure to reduce the uncertainty? Because I think the uncertainty is the thing that's making it quite difficult for people to grasp.
Yeah, we might start with Caroline and then with Gerard, then I think we'll finish up then. So Caroline, do you have a response to that?
Yeah, sure. So my opinion on this is that meteorology inland, where you can see everything and it's easy to access sites, there's a really, really good system in place for observing the atmosphere. We need a similar equivalent type system in the ocean, and we need to enhance and improve what we're already doing and do it consistently over forever, for decades, so that the information is there when something happens, that you can actually have the right, robust data to be able to analyze and give a very solid answer to whoever needs it.
Very good, Caroline. Thank you so much. Tito?
Yeah, I think we actually just had an Irish AMOC conference, and so we were. So a result of this was also where measurements should be improved. So it was said that in the Labrador Sea, which is one of the partial tipping points, there it would be very important to measure the three-dimensional structure, and if there's more convection happening or less convection happening. That is one of the major points, the Labrador Sea. But also even here directly in front of our doorstep, west of Ireland, to see actually the extent of this subpolar gyre, not just on the surface, where of course we have the warming from the atmosphere because of the greenhouse gas impact, but also a little bit deeper down west of Ireland. In how far do we see there, for example, a cooling trend of this North Atlantic warming hole that you, Jared, mentioned, or also dubbed as cold blob?
The cold blob, yeah, I love that name. Jared.
So I suppose definitely, I think we can always improve our observational system. So even we can take the gold standard in terms of measuring the overturning circulation is the system of moorings that's deployed between the Canaries and the Bahamas. Now, it's very hard to sustainably fund observations like that, and we heard in our AMOC conference from the head of the RAPID project how he's being put under pressure in terms of kind of modifications to that. So basically, any observations that would be cheaper to implement, any observations that would give more direct information. So, for example, those moorings are recovered every 6 to 12 months in terms of the turnaround. So there's quite a lag in terms of when you get it. So there's always observational gaps that can be filled there. In some sense, the biggest challenge in terms of AMOC is that the time series is short. So that rapid time series is still only 20 years. In climate circles, we talk about 1.5 degrees. When people are talking about 1.5 degrees as the Paris climate targets, they're talking about 30-year average being 1.5 degrees. So, that's one data point. That's long. It takes more data than we ever gathered for the AMOC, more or less. So that kind of extension in time in terms of understanding the dynamics and how we can use past data to understand the AMOC is really critical. And then there's an understanding in terms of the variability that we do measure. So, one of the things we've seen in those gold standard measurements is that you get everything in there. So the wind blows and you see the ocean, respond, and that responds all the way down to the deepest parts of the ocean. But that's not AMOC in a climate sense. So it's understanding these kind of layers of variability as well is really critical. So both a kind of a physical observational gap, but also an understanding gap as well, I think.
Well, a huge thank you to our panel, and thank you so much to Caroline joining us remotely. Under these circumstances, Tito and Jared.